we can use fast Fourier transforms in the same applications as DFTs, but they're much less resource intensive and can be done by a computer much more quickly. Let's say your boss needs you to design a system to remove noise from a signal. On top of that, the system needs to be very quick and use very few resources. Here, I have three sinusoids, 50 Hz, 100 Hz, and 150 Hz. We're going to add a bunch of noise to this signal until it's completely unrecognizable. Now our goal is to try and reconstruct the original signal without knowing what frequencies are hiding in here. So here's the plan. We're going to take the fast Fourier transform of our signal, and we're going to find the power associated with each of those frequencies. If that power is below a certain threshold, it should be filtered out as it's probably noise. Then, with the remaining frequencies, we're going to take the inverse fast Fourier transform and get our original clean signal. So here's our noisy signal. We don't know what frequencies are hiding in here yet. If we take the fast Fourier transform of this signal, we're going to get it in the frequency domain, which gives us a complex value for each frequency. Let me remind you what the equation is for power in the frequency domain. But we only want power for each frequency on its own. So that some part's going to disappear, and that just leaves us with the magnitude squared of each complex coefficient. Now if we plot the power for each of our frequencies, we get the following graph. You can clearly see spikes around 50 Hz, 100 Hz, and 150 Hz. These are the frequencies we're looking for. If we filter out all frequencies below the power threshold, we'll be left with the Fourier transform of our original clean signal. Now if we perform an inverse fast Fourier transform, we should be left with our original crisp clean signal. And that's what we see right here.